This is SpaceTime, Series 24, Episode 13. Coming up on SpaceTime, strange new clues about how stars are made, understanding the secrets of neutron stars, and Iran's latest nuclear missile test. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered some strange new clues about the processes involved in creating a star. It sounds like a contradiction in physics, but astronomers have detected cold ionized hydrogen towards the centre of the Milky Way galaxy. The thing is, ionization usually occurs under extremely hot conditions at temperatures of tens of thousands of degrees Celsius. It's these extreme conditions which provide the high energies needed to strip negatively charged electrons from their atoms, leaving the atoms ionized with a positive electrical charge. But this discovery, reported in the monthly notices of the Royal Astronomical Society, was detected in a cold molecular cloud at temperatures of minus 230 degrees Celsius. While the possible existence of cold ionized gas had been hinted at in earlier observations, this is the first time astronomers have clearly detected it. The new discovery may even help explain why stars don't form as quickly as they theoretically could. Normal energy sources, such as photons from massive stars, wouldn't cause this. But more exotic forms of energy, such as high-energy particles created in supernova shock waves near black holes, could provide a more likely source. The findings also demonstrate how the energy needed to ionize hydrogen atoms can penetrate deep into cold clouds. And these cold molecular gas and dust clouds are the places in which new stars are born. In our own galaxy, we know that stellar birth rates are incredibly slow, just one solar mass star per Earth year. And that's much lower than what we see in surrounding galaxies. Now, it is possible that the energy observed here is acting as a sort of stabilizer for cold clouds, preventing them from collapsing in on themselves to generate the temperatures and pressures needed to form new stars. One of the study's authors, Associate Professor Randall Waite from the Curtin University node of the International Centre for Radio Astronomy Research, says the observations were only made possible because of the wide bandwidth of the prototype Engineering Development Array, which is part of the upcoming Square Kilometre Array project. The low-frequency portion of the Square Kilometre Array is being built in an extremely radio-quiet location in outback Western Australia, which is already home to the Murchison Wide Field Array Radio Observatory. Once fully operational, the Square Kilometre Array will be the world's largest radio telescope, spanning both the Australian outback and parts of southern Africa. Waite says these findings are providing astronomers with a glimpse of what the SKA will be capable of once it's built.
The Engineering Development Array it's an array of 256 what we call dipole antennas, which are spread out over 35 metres. And they work, even though they're individual antennas, they work as a single large antenna. So we built this as a sort of prototype system for future Square Kilometre Array, low-frequency array technology. And it's actually a hybrid system. It's built out of MWA dipoles, which is actually a separate radio telescope, but in the configuration of the proposed future SKA low. So the entire system is a large aperture array. All of the signals from all of the dipoles are combined together electronically, and it works effectively as a large single, you can think of it as like a large single dish, but where there are no moving parts, and it's pointed electronically to different places on the sky.
How do you do that?
So if you think about a large single dish, it's mechanically pointed to the object in the sky that you want to look at. And the radio waves bounce off the dish and are reflected to a focal point where there's a single receptor that receives those radio waves. So instead of having a large mechanical dish, what we do is we have many inexpensive radio receptors that sit on the ground. There's no moving parts in these, but each of these is still receiving the same radio waves. And instead of having a large mechanical dish that focuses the waves for a single point on the sky, we can introduce some delays in the system that effectively point this system to any place on the sky. So it's all electronic, and it's done via really high precision introduction of time delays in the signals, such that when they're all added together, it acts like a single large receptor.
Exactly what are you picking up? Obviously radio waves at very low frequency, but also, I believe, very high resolution.
Yeah, so this single antenna basically has the same resolution as the equivalent large dish of the same size. So it has the same resolution as a big 35-metre dish would be if you actually built it out of steel and were pointing it on the sky. As a single dish, the resolution of this system, it's fairly modest. It's a sort of degree scale. But when you combine many of these systems into a very large telescope array that's spread over many tens or even hundreds of kilometres, the angular resolution of these systems can be really quite extraordinary. We're talking about milli-arc-second angular resolution here, which is actually better than any optical telescope can achieve. The other dimension of resolution that we have with this telescope that's quite unusual is the frequency resolution. So we use this with very, very fine frequency resolution to look at signals from the galactic centre. And when you have fine enough frequency resolution, you can pick out faint signals that are generated by the ionized gas that exists in the galactic plane in between us and the centre of the galaxy. And this ionized gas can create an extra amount of signal, or it can absorb some of the signal that's coming to us from between us and the galaxy. So those are sort of the two dimensions of resolution that we have with this system.
And it was this which allowed you guys to find this ionized hydrogen gas right smack bang in the middle of these cold molecular clouds.
That's exactly right. So we really need the fine frequency resolution in this system, and we need to be able to see the full range of frequencies from the lowest radio frequencies down around 30 megahertz all the way up to 300 megahertz, because the signals that we're looking for here are very, very faint, and by combining a number of them together and using the appropriate fine frequency resolution, we can actually detect these things. It's actually quite difficult. They're very, very faint signals. We're talking about less than 1 part in 1,000 kind of difference. But with, sufficient resolution and sensitivity, you can do this. And so what we've detected is emission from ionized hydrogen at the lowest ever radio frequencies. And the reason why this is significant is because at these very, very low frequencies, we can put an unambiguous upper limit on the temperature of this gas, and we find that it is quite cold. So it's cold ionized gas, and we speculate that it's originating in a well-known nearby gas cloud that is in between us and the centre of the galaxy.
This gas is around minus 230 degrees Celsius, and normally when you think of ionized gas, it's like 10,000 degrees and more.
Exactly. So what we think is going on is that this gas is associated with the skin of some very cold gas clouds that are between us and the galaxy, and the skin of these clouds gets ionized by the ambient radiation field, but the radiation field's not strong enough to heat up the gas, and it sort of forms this self-shielding state of equilibrium where the gas can remain cold but partially ionized. And that makes all the difference. Not something that you would normally think of, like you say, as like on the surface of the sun or something like that, where it's a very, very hot system where it's the physical temperature that ionizes the gas. In this case, we think it's much more likely to be associated with the ambient radiation field, ultraviolet and X-rays and things like that are just out in the interstellar space.
With this new array, this is very much a prototype, I take it, for what's going to be happening over a large part of the low-frequency area of the square kilometre array. How many more of these patches, cells, are likely to be built?
In SKA terminology, what we built is the equivalent of a station. We call it a station, which is 256 antennas all working as a single unit. The full SKA-1, which is the one that we're planning to start construction in a couple of years, that will consist of 512 of such stations. So altogether there'll be about 131,000 dipole antennas, and these are spread out over about a 40-50 kilometre diameter of the Western Australian desert.
And then they all fed into their own optical fibre cables going back to a central collection point and then down to Perth?
Yeah, that's exactly right. The signal from each antenna goes via optical fibre. At some point it will be digitised and all all of the signal processing is done digitally. Some of the processing will be done on site, and yes, then the data will make its way down to Perth or somewhere else for subsequent processing.
You guys are at the Murchison Radio Astronomy Observatory site in Outback, WA. There are a couple of antennas being built there. There's ASCAP, there's what you guys have.
Correct.
Tell me about the sort of variety there.
Yeah, the observatory hosts two large instruments. So one of them, as you say, is the ASCAP array. The other one is the Murchison Wide Field Array, which is a sort of low-frequency precursor to Ska, but it's also an operational productive scientific instrument in its own right. The observatory also hosts a number of smaller experiments. Probably the most famous of the smaller experiments is the EDGES experiment, which made the first detection of a signal from cosmic dawn. That's quite a significant experiment. So there are a number of smaller ones. Others include some cosmic ray detectors and things like that. So the site hosts a number of these instruments. It's a pretty amazing site because it's quite far away from the nearest population centre. That means that it's very radio quiet. The kind of frequency ranges that most of the instruments there work in would be absolutely overwhelmed by TV and FM radio broadcasts if they were any closer to a city. So it's very radio quiet, and it has very, very good protections in place both at the state and federal government levels to keep that site quiet.
And of course, there are very specific radio frequency windows you're looking at. That still pose a problem with things like satellites, and we've got a new satellite constellation now being put into orbit by SpaceX, something like 70 satellites at a time. They're going to be like 12,000 of them eventually, and I believe there could be some issues with the frequency bands.
Yeah, satellites are ever encroaching on of the radio astronomy spectrum. For our particular experiment, those satellites are working at a different frequency, but they could be a big problem for ASCAP. They are certainly a big problem for other radio telescopes working at other frequencies. So for us, there's a number of existing satellites that come over. They're weather satellites and communication satellites and things like that. And they are very strong emitters, relatively speaking. So, these low Earth orbit communication satellites are a problem, and we're working on ways to mitigate that. It's a case of, as long as they're not so strong that they overload the system, then we have a chance of being able to remove the signals and try and recover parts of the spectrum. But they are a problem, certainly.
And I guess that's one of the things the computer programs are going to have to do, the programs that are going to be sifting through the data before the scientists see it.
Yeah, absolutely. So one of the first tasks that we have in the sort of data production pipelines is a sort of a triage step to look at the initial data quality. So if there's really, really strong interference in there, then we might just flag that as bad or unusable and try and reobserve the sources. One of the things that we're trying to do is look at active mitigation techniques. For instance, if we can have a separate antenna that looks at a known interfering source and tries to subtract that signal out. It's very much a open research question. We're not 100% sure we can pull it off, but that's one of the things that we're looking at. And we certainly try to identify and remove as much of this interference as we can before it goes downstream to the science teams.
That's Associate Professor Randall Waith from the Curtin University node of the International Centre for Radio Astronomy Research. And this is SpaceTime. I'm Stuart Gary. Still to come, understanding the secrets of neutron stars, and Iran test fires a nuclear-capable missile. All that and more still to come on SpaceTime. Okay, let's take a break from our show for a word from our sponsor, Namecheap.com. As their slogan says, search and buy domains from Namecheap at the lowest prices. Now, this is the service that our team at Bytes.com use to buy and manage our domain names, and we're really happy with the service, support and value we're getting. Buying the right domain name shouldn't be hard, and with Namecheap, we've found it to be anything but that. And you can find your dream domain and join over 2 million happy customers when you register with Namecheap. Trusted with well over 10 million domains, you'll know you're in safe hands when it comes to turning your website idea into reality. And they've got some excellent tools to help you find the right name, like the handy search engine. All you do is type in your desired name, cross your fingers, and press search. And if what you want's already gone, and it does happen sometimes, they'll come up with some great alternative ideas. And if you're looking for some new inspiration, try the new website domain name finder, Beast Mode. It'll help you discover thousands of domain names fast. We've found their prices to be excellent, management tools intuitive, and they're easy to use with excellent custom support if you need it. All in all, it's a great experience all round if you're looking to pick up a domain name or two. So, why not check them out and help support our show at the same time? Just visit spacetimewithstuartgary.com/Namecheap. That's spacetimewithstuartgary.com/Namecheap, and Namecheap is one word. You'll find the URL details in the show notes and on our website. Just visit the support page. That's spacetimewithstuartgary.com/Namecheap. And now, it's back to our show.
You're listening to SpaceTime with Stuart Gary.
Scientists have found evidence of alpha particles on the surface of neutron-rich heavy nuclei, a discovery which could provide new insights into the structures of neutron stars, as well as the process of alpha decay. Alpha particles, also called alpha rays or alpha radiation, consist of 2 protons and 2 neutrons bound together in a particle which is identical to a helium-4 nucleus. Neutron stars are among the most mysterious objects in the universe. When stars, such as our Sun, reach the end of their lives, having fused most of the hydrogen in their core into helium, the balancing act between gravity crushing a star towards the centre and the nuclear energy pushing outwards ends, and gravity wins. Now, this additional mass crushing down on the core causes a dramatic increase in pressure and temperature, eventually triggering a helium flash, making it hot enough for the core to begin fusing helium into carbon and oxygen. At the same time, a hydrogen shell begins to burn surrounding the core, and the star's outer layers expand due to this increased heat, and because it's now further away from the core, the outer envelope also cools. This combination of expansion and cooling transforms the star into a red giant. Now, eventually, stars like our Sun fuse most of their core helium into carbon and oxygen. But they don't have enough mass to fuse carbon and oxygen into heavier elements, and so the fusion process ends. The outer gaseous envelopes form a planetary nebula, leaving the stellar core exposed as a white dwarf, which will slowly cool over the eons of time. However, stars far more massive than the Sun face a very different fate. Because they're so massive with higher core temperatures and pressures, they fuse hydrogen into helium through a different process, and they go on to fuse progressively heavier and heavier elements: carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, nickel, and eventually iron. But no matter how massive a star is, stars don't get massive enough to fuse iron into heavier elements. And so the balancing act between gravity crushing a star down towards its centre and nuclear energy pushing outwards reaches a final conclusion. And once again, gravity's the winner, causing the star to collapse in on itself in what's known as a core collapse supernova. For stellar cores greater than approximately 1.44 solar masses, a figure known as the Chandrasekhar limit, this immense gravitational collapse breaks through electron degeneracy. That's the quantum mechanical effect arising from the Pauli exclusion principle, which prevents more than one fermion, such as an electron, from being in the same minimum energy quantum state at the same time. Instead, it allows further collapse, crushing the negatively charged electrons and positively charged protons together to form neutrons, hence the star's name. Although only a dozen or so kilometres wide, neutron stars are the densest objects in the known universe, other than black holes. In fact, just a sugar cube-sized piece of neutron star material would weigh 100 million tonnes. And believe it or not, matter in the nucleus at the centre of normal atoms exists at similar densities to that found in neutron stars. One of the study's authors, Junki Tanaka from the Technical University of Darmstadt in Germany, says understanding the nature of matter at such extremes is important for science's understanding of neutron stars, as well as the beginning, workings and final fate of the universe. Intriguingly, despite their vast difference in size and mass, the tiny atomic nuclei found on Earth and the enigmatic neutron star found in space are actually governed by the same type of interactions. This connection's been well established by scientists through the nuclear equation of state, which describes the relationship between density and pressure of nuclear matter. The new findings, reported in the journal Science, examined 10 nuclei and found evidence of alpha clusters, groups of 2 protons and 2 neutrons in heavy nuclei. Now, the authors examined a series of neutron-rich isotopes of tin, ranging from tin-112, which is only 62 neutrons, to tin-124, which is 74 neutrons, and so has a much thicker neutron skin. The authors deliberately knocked out alpha particles from the nuclei by bombarding them with protons, and they then examined how frequently they were able to observe alpha particles in progressively heavier isotopes. They identified the clusters in the very surface region of the neutron-rich tin atomic nuclei, implying that the so-called neutron skin isn't purely neutron matter as the name implies, but also includes alpha clusters. Importantly, they also discovered that the effective number of alpha clusters decreased gradually along with the number of neutrons. They theorized that this is due to the interplay between alpha cluster formation and the thickness of the neutron skin that surrounds the nucleus. The findings have important implications both for science's understanding of the nuclear equation of state and for understanding neutron stars. In the near future, more and more accurate data on the bulk properties, mass and radius of neutron stars should become available both through electromagnetic and gravitational wave observations. The present work is also a key step towards fully understanding alpha decay, the type of radioactive decay in which atomic nuclei spontaneously emit an alpha particle. It was about 90 years ago that physicist George Gainer famously proposed that alpha decay takes place due to the quantum tunneling of alpha particles or clusters. However, while the theory was generally accepted, it's never been shown conclusively that these clusters actually existed in heavy atoms. So the findings of this new study that alpha clusters do exist on the surface of heavy nuclei could provide an answer to that question of the origin of alpha particles in alpha decay. This is SpaceTime. Still to come, Iran carries out a successful test of a nuclear-capable missile, in the process performing yet another breach of its own nuclear weapons ban treaty. And the SpaceX SN9 Starship test article prototype crashes and burns during an explosive landing. All that and more still to come on SpaceTime. Iran says it successfully carried out a missile test. The launch marks yet another breach of Tehran's nuclear weapons ban treaty, the 2015 Vienna Accords, which were ratified by the United Nations Security Council under Resolution 2231. The treaty specifically prohibits the Islamic Republic from developing missiles capable of carrying nuclear warheads. The missile was launched from central Semnan province, where Iran has a top-secret missile launch complex. Tehran claims the 25.5-metre tall Zolshanar-1, which was used for the test, is equipped with 1 liquid and 2 solid fuel stages and is designed to be flown from a mobile launcher. It says the missile is capable of carrying a 220-kilogram payload into a 500-kilometre high sun-synchronous low Earth orbit. It's the latest in a growing list of violations by the Islamic Republic, which security experts believe is part of a pattern to secretly develop nuclear weapons and the long-range missiles needed to deliver them. Tehran recently tested a new MIRV, or Multiple Independently Targetable Re-Entry Vehicle warhead. MIRVs are used by missiles carrying multiple thermonuclear warheads. The International Atomic Energy Agency says the Islamic Republic's also explored various fusing, aiming and firing systems designed to make its missiles more capable of reliably delivering a nuclear warhead. The program centers around several missiles based on North Korean technology. The two rogue states have been secretly working together on parallel nuclear weapons and delivery system programs. For Tehran, these include the two-stage Safir missile, which is based around the Shahab-3 long-range ballistic missile, which itself is derived from the North Korean Nodong-1 and Hwasong-7 missiles, which are based on Soviet Union-era Scud missile technology. These weapons can deliver a 1,200-kilogram warhead or 5 MIRV, or independently targetable multiple re-entry vehicle warheads, over a distance of 2,500 kilometres. The first stage is believed to use a single fixed turbo pump fed thrust chamber with 4 graphite vanes extended into the exhaust to provide steering. The liquid fuel propellants may include unsymmetrical dimethylhydrazine or a kerosene-gasoline mix burned with a storable oxidizer. The second stage is thought to use similar propellants burned in a cluster of possibly 4 small thruster chambers fed by a single turbo pump. The larger, more powerful 27-metre tall, 2.5-metre diameter Sophia 2A, or Seymour ballistic missile, weighs 87 tonnes. It uses a North Korean Taepyeong-2 ballistic missile for the first stage, which combines 4 Scud SS-1 Egyptian Scud-B or Chinese Scud-C missile rocket motors, with steering provided by 4 small vernier engines. The upper stage uses the Shahab-3 missile we mentioned earlier. Last month, European powers raised concerns over Iran's plans to produce uranium metal, warning that Tehran has no creditable civilian use for the element. The joint statement by the British, French and German governments warned that the production of uranium metal has potentially grave military implications. The International Atomic Energy Agency says the Islamic Republics confirmed that it is advancing research on uranium metal production, claiming it was for a research reactor in Tehran. Producing or acquiring plutonium or uranium metals or their alloys would be another violation of the 2015 Vienna nuclear deal agreed to by Tehran. The United Nations nuclear watchdog's also concerned about a missing metal disk of uranium, the type used in thermonuclear weapons, and the location of other undeclared nuclear material that's been missing since Tehran began nuclear weapons research activities. The latest developments follow recent revelations that Iran's enriching uranium up to 20% purity. That's well beyond the 3.67% it agreed to under the 2015 United Nations Nuclear Non-Proliferation Treaty. Tehran also recently doubled the number of advanced centrifuges it operates, and it's begun introducing IR-9 centrifuges, which is some 50 times faster than those agreed to under the 2015 accord. Iran also recently switched on a new chain of 30 IR-6 centrifuges at its Natanz nuclear facility, thereby doubling the number of working centrifuges there to 60, and allowing Tehran to dramatically increase daily enriched uranium production. All this comes despite the fact that under the Islamic State's nuclear deal, Tehran's limited to only first-generation IR-1 centrifuges. Centrifuges are key. They enrich uranium by rapidly spinning uranium hexafluoride gas, separating out the fissile uranium-235 from the non-fissile uranium-238. All this has allowed Iran's stockpile of enriched uranium to skyrocket to more than 12 times the limits it agreed to under the Vienna Accord. Tehran's also prevented United Nations nuclear watchdog inspectors from entering several sites suspected of containing undeclared nuclear material and nuclear-related activities, yet another breach of the 2015 treaty. Through all this, the oil-rich nation insists its nuclear program is exclusively for peaceful power generation purposes. Latest estimates suggest Iran now has enough enriched uranium for at least 2 nuclear weapons. This is SpaceTime. Still to come. SpaceX's SN9 Starship test article prototype crashes and burns during a test. And later in the science report, Novavax says its new COVID-19 vaccine has demonstrated 89.3% efficacy in UK Phase 3 trials. All that and much more still to come on SpaceTime. After what looked like a flawless launch and climb to altitude, SpaceX's SN9 Starship test article prototype has crashed and burned during an explosive landing attempt at its Texas test site. It was the latest in a string of failed landings for the gleaming stainless steel next-generation mega rocket. Its predecessor suffered a similar fate back in December. The SN9 launched smoothly and progressively shut down its engines as planned as it reached its target altitude of 10 kilometres. The spacecraft then performed a series of test manoeuvres, culminating in a planned horizontal return to Earth. Unlike the Falcon 9, which re-enters Earth's atmosphere tail first and then maintains this orientation all the way down to the surface for a vertical landing, Starship will re-enter horizontally like the Space Shuttle, using its underbelly as a heat shield. But instead of landing horizontally on a runway like the shuttle, Starship needs to undertake a last-minute manoeuvre to reorientate itself vertically, so it can land tail first, just like the Falcon 9. And that's where the problem is. As with the last attempt in December, it came down too fast, without enough time to correct a bad approach angle. Flaps weren't able to control the error, and the spacecraft came crashing down in a deafening explosion and bright orange fireball.
We are counting down for today's 10-kilometer test flight. We are currently loading liquid methane and liquid oxygen propellants onto Starship. Today's flight will be similar to our previous flight last December. Continuing to count down on the flight of Starship serial number 9. Propellant loading is complete. Next event is retract of the quick disconnect from the flight vehicle.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
All three Raptor engines got power. Starship climbing to 10-kilometer altitude. 3 Raptor engines burning. Everything continues to look nominal right now for the stage and for propulsion. Just passing through 3-kilometer altitude. Next major event is shutdown of engine number 3. Flight continuing on Starship. As a reminder, this is a test flight to a 10-kilometer altitude. Engine number 3 shut down on time as planned. We're continuing to climb on 2 engines. Everything continues to go well with Starship.
Good engine performance so far. T2 shut down.
T plus 3 minutes, 20 seconds. We've shut down engine 2 on time. Starship now climbing on the power of engine number 1. Headed to the 10-kilometer altitude. T plus 4 minutes. Vehicle is at 10 kilometers. It is at apogee. We're continuing to throttle down engine number 1 to hold altitude. We're preparing for handover on the propellant tank. 4.5 minutes. We are handing off to the LOX tank. We are beginning to flip to horizontal. In the white cloud, there is a liquid oxygen dump. We've now transitioned to horizontal and beginning the subsonic test portion of the flight, where we check out the aft and the forward flaps to hold the vehicle stability as we descend back to the landing pad. T plus 5.5 minutes. Starship continuing the subsonic descent, using the forward and aft flaps to control its attitude as we come back down to the landing pad. Everything continuing to go well in this portion of flight.
Land intro.
6 minutes, 10 seconds into flight. We're down beneath 1.5 kilometers. We're preparing to restart 2 engines, flip the vehicle vertical, then transition to 1 engine for the landing burn.
Oh, I see. Let's get cameras up.
Rolling to anomaly net and opening 3.911 at this time. We will start sweeping for fires.
We had, again, another great flight up to the 10-kilometer apogee. We demonstrated the ability to transition the engines to the landing propellant tanks. The subsonic reentry looked very good and stable like we saw again last December, so we've got a lot of good data on flap control. And again, we've just got to work on that landing a little bit, but we'll find out from the team as they go through the data. We were in contact with telemetry all the way down. So all told, another great, and a reminder, this is a test flight, second time we've flown Starship in this configuration. We've got a lot of good data, and the primary objective to demonstrate control of the vehicle in the subsonic reentry look to be very good, and we will take a lot out of that.
Of course, the crash landing is not necessarily a setback. That's because it's allowed engineers to gather valuable data about the spacecraft. After all, space is hard, and rocket manufacturers are well known for losing rockets during early testing as they explore their new designs. Originally called the BFR, or Big Falcon rocket, Starship is the culmination of Elon Musk's dream to develop a fully reusable super heavy lift spacecraft capable of carrying 150 tons of people and cargo into orbit and 100 tons on missions to the Moon, Mars, and interplanetary journeys across the solar system. Musk sees his Starship as a colonial transport system. Now, technically, Starship's only the upper stage of a 2-stage launch system. The 230-ton first stage, called the Super Heavy, is 68 metres long, 9 metres in diameter, and constructed out of gleaming stainless steel. It'll be powered by 37 liquid methane and oxygen-propelled Raptor rocket engines, providing 72 meganewtons or 16 million pounds of thrust. The 120-ton upper or Starship stage will be 50 metres long, still 9 metres wide and constructed out of stainless steel and powered by 6 liquid methane and oxygen propellant Raptor rocket engines, 3 atmospheric and 3 vacuum, delivering approximately 12,000 kilonewtons or 2,600,000 pounds of thrust. Refueling tanker and satellite payload delivery upper stage versions will also be produced. Ultimately, SpaceX plans on using its Starship Super Heavy launch system to replace the company's existing Falcon 9 and Falcon Heavy launch systems, as well as its Dragon capsules, during the early 2020s. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. Novavax, the third vaccine the Australian government's committed to purchasing, claims its new COVID-19 vaccine has demonstrated 89.3% efficacy in UK Phase 3 trials. Federal government's pre-ordered 50 million doses of Novavax. Unlike the modified RNA Pfizer vaccine, which uses a snippet of the coronavirus genome to encourage antibody production, and the Oxford AstraZeneca vector vaccine, which uses a less harmful adenovirus to transport a coronavirus protein spike and trigger an immune response, Novavax is a recombinant vaccine based on the entire SARS-CoV-2 spike protein produced in insect cells, plus an immune system activating adjuvant. Professor Rhianna McIntyre, head of biosecurity with the University of New South Wales, says the Novavax findings also provide the first confirmation that clinical efficacy is reduced against some variants of the original COVID-19 virus. The data shows 95.6% efficacy against the original China coronavirus, but only 85.6% against the B117 UK variant, and just 60% in South Africa, with the B1351 variants dominant. The virus, which is believed to have accidentally escaped from the Chinese Academy of Sciences Wuhan Institute of Virology laboratories in the last quarter of 2019, has now killed some 2.3 million people and infected over 105 million others. A new study warns that the Earth is losing ice at a record rate. A research team, first to carry out a survey of global ice loss using satellite data, has discovered that the rate at which ice is disappearing across the planet is speeding up. The findings, reported in the journal Cryosphere, show that 28 trillion tonnes of ice was lost between 1994 and 2017. That's equivalent to a sheet of ice 100 metres thick covering the entire United Kingdom. Scientists using data from the European Space Agency's ERS, ENVISAT and Cryosat satellites, as well as from the Copernicus Sentinel-1 and Sentinel-2 missions, found that the rate at which the Earth has been losing ice has increased dramatically over the past 3 decades, from 0.8 trillion tonnes a year in the 1990s to some 1.3 million tonnes per year by 2017. The increase in ice loss has been triggered by warming of the atmosphere and oceans, which have been heating up by 0.26 degrees Celsius and 0.12 degrees Celsius per decade since 1980. The United States Air Force says its new B21 Stealth Bomber should be starting its flight tests by the middle of next year. At least 100 B-21s have been budgeted for by the Pentagon at a cost of $80 billion. The US Air Force Global Strike Command expects ultimately to have up to 200 B-21 Raiders in service, replacing current squadrons of B-1, B-2 and B-52 aircraft. The new Northrop Grumman-built long-range strike bomber is similar in appearance to the existing flying Batwing-shaped B-2 Spirit stealth bomber, but relocates its 4 engines closer to the wing root next to the fuselage. Its air intakes are angled rather than serrated as those on the B-2, and it uses over-wing exhausts to mask its infrared signature, unlike those on the Spirit. The B-21 is designed as a very long-range, large, heavy payload stealth aircraft, capable of delivering both precision-guided conventional and nuclear weapons. New research shows that the brains of musicians have stronger structural and functional connections compared to the brains of non-musos. The findings, reported in the journal J Neurosci, also suggest that musicians who begin their training at a younger age also had stronger structural connections than musicians who started later in life. The authors say the results demonstrate how experience really does shape the brain, especially in early life, and how enhanced musical skills are represented in the brain. To quote the immortal Dr. Sheldon Cooper, There's absolutely no scientific evidence to support clairvoyance of any kind, which means that fortune-telling is a fraud, the profession is a swindle, and its livelihood is dependent on the gullibility of stupid people. So, in a world full of shongsters and con artists, everyone needs a gimmick to stand out from the crowd. And one clairvoyant has decided that throwing asparagus in the air, like you just don't care, is as good a way as any. Tim Mendham from Australian Skeptics has the story of magic veg.
Jemima Packington is a British psychic, and I always put psychic in quotes, okay? So she's a British psychic and is obviously looking for a gimmick. So rather than just using a crystal ball or cards or something like that, or sticking her fingers on her head to help her visualise things, she throws asparagus stalks. She actually says she throws asparagus tips, but the photos show her with stalks, but never mind. Which is a bit like I Ching, where they throw the sticks and you see patterns and you gauge those patterns. So here she is throwing down asparagus tips or spears or stalks or whatever you like to call them, and she's making predictions.
I guess you could do the same thing with tea leaves or chicken entrails and things like that, whatever you wanted.
Well, they do, don't they?
Exactly.
Or jacks. If every person who plays, the jacks game with the knuckles and throws them in the air and tries to catch them on the back of the hand, that'd be a great source of predictions. Actually, I don't know why anyone hasn't done that. Oh, I might copyright that one, so I'll put that one forward as Jacksology. But Mystic Veg, as she's referred to, I don't think very seriously, throws these things up in the air and makes predictions, and she's making such earth-shattering predictions as people will be nicer once coronavirus pandemic lockdowns are finished. There will be some ill health among royals. Really?
How old's Her Majesty now? It's 94.
Yeah, no, I know. There's bound to be some ill health somewhere.
Philip's even older.
Yeah, that's right. And she divorces and things, but they actually asked her for some specific predictions for Australia.
Right.
And it might be nice to know that travel between the UK and Australia will be back open again before June. The banks will have wobbles. Whatever that means. And Rafael Nadal will not win the Australian Open. So you keep those up your sleeve. And
they're sort of both a combination of the scattergun approach, where you make a whole lot of predictions in the hope that one of them might have a hint of bullseye target on it, but at the same time, people will forget all the other ones.
Yes. Exactly, and then they'll trade off that for the rest of their lives. I'm the one who predicted the assassination of Kennedy, or the attempt on Ronald Reagan's life, or Rafael Nadal not winning the 2021 Australian Open. And so, you throw out a lot of these things. Some of them are vague, like royals getting sick. You think, oh yeah, thanks, and that sort of stuff. And banks having wobbles, they probably will. And then you throw in a few specific ones for good measure, just to show how good you are before they even come true or not. People think, well, that's impressive. You got so specific, and then if they don't come off, you forget them, and if they do, you say, see, I got that one right. The Australian Skeptics, being the spoiled sports that we are, under Richard Saunders, who's a quite well-known skeptic and figure in the skeptical world, is running a project which has grown and grown and grown over the years of actually keeping tabs on psychics' published predictions, a lot of them in women's magazines and that sort of stuff, especially at the start of the year. They often make predictions for the coming year, and he's actually taken note of these, and with a big crew of volunteers who obviously have more time on their hands than some of us do.
You've got to start publishing these. I've been looking forward to these for ages now.
I know. Well, I have news for you. We're going to sort of publish an interim report in the next issue of our magazine.
Excellent.
So everyone should subscribe to the Skeptics straight away, skeptics.com.au, and you'll actually see. But there are tens of thousands of these things, and it's taken them a lot longer than they thought because they keep finding more. And sort of being the obsessive sorts and the dedicated to true research and completeness, they're trying to include everybody in there. And they classify them as against obvious. A volcano will go off somewhere in the world, to vague. I have, someone somewhere might be ill, to the very specific ones, and to see how they work out. Some of them are easier to track down than others to see if the prediction actually came true. Others a bit harder, but as much as they can, this project is looking at thousands and thousands of these predictions. And from the latest count I've heard, about 90% of them are way off, and the rest are too vague to even worry about. In other words, they're not doing very good, and if your car mechanic or neurosurgeon was only right 10% of the time, I would go somewhere else.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.